Thank you, Dewi. So Jose here, co-founder of FX and Chief Scientific Officer. So today is the second webinar, and today we are going to explore how to make the best muffin. So this is a toy example that we will be looking at. This is the second webinar of a series of several, and that they occur every month. And let's get started. So since we are a few people, please, if you have any question, just ask, and they will take care of the questions and make them. So overview, we're going to start with an industrial challenge of a makeup company that is related to strategic data acquisition or design of experiments. We will then move to compare trial and error versus systematic experimentation. So an intuitive way of gathering data versus a systematic manner. Then we will recap the design of experiments flow. This is the 5 phases of a successful design of experiments project. And we will apply it to the muffin recipe optimization experimental design and analysis. We will end the webinar with a quick software demo where we will highlight some of the aspects. So let's get started. Make Me a Muffin Limited Company has a history that you see in this timeline. So it has been a successful story until now. How did it start? So it kicked off in 2005. John and Marie developed a really tasty recipe for muffins. And in 2010, after their kids could not eat more muffins, but they found them really delicious, they founded a company and opened a small shop. Things were going well. 2015, production scaled up, and they purchased a large muffin machine. 2 years later, in 2017, they decided to leave their jobs to focus on the company. But then COVID came and changed their business. So they could not sell in their shop anymore. So they reconverted themselves and they changed their business to deliver muffins, and they closed the shop. That moved them to purchase an automatic production line for muffins in 2023, as they were already providing muffins to large supermarket chains and so on. But what happens then? That they had to to go to different providers for the flour, and the different batches of flour affected the quality of the muffins because the flour characteristics, they differed. So they had different content of proteins, different content of starch, or different moisture. And as a result, some of the batches were not having the quality they used to, and the orders started to be rejected. So they ran into problems. So it is known that the variability in the flour affects the quality of the muffin, but they don't know how. And of course, they cannot afford to have more rejected orders. So it's a lot of waste material, but also a huge economic loss. Because oftentimes full production batches are discarded. So how they did fine-tune the recipe of the muffin before? Using trial and error. So they had, of course, a lot of experience and know-how on how to make muffins. And they were just adjusting the recipe to get the end result they wanted. But in an automatic production line, that is not so easy because experimentation involves stopping production. And in that setting, trial and error can be highly inefficient. Plus, they cannot tune the recipe and the machine parameters for each batch of flour that will arrive to the factory. So they need systematic experimentation, and they need to have a more robust process so that they can cope with the variability of the flour and assure that the end product, so the muffins, will have always the best quality. So let's see what is trial and error and what is systematic experimentation. And to see that, we have here a toy example with two input factors. So we have factor 1, which is time, that is expressed in minutes and changes from 25 to 40. And the second factor is temperature and changes from 175 to 225 Celsius. And the process quality in this toy example is measured using a single numerical quality attribute, being that goes from 0 to 100, and 100 is the best value for it. So objective is to find best values for time and temperature such that the process quality is maximized. So just a learning bite here. When you are about to study a problem where you have some inputs and some outputs, it is very crucial to identify the influential factors, but also set the range that you are going to study those factors. So it is important to set a range that is not too narrow, so you may lose interesting phenomena that may happen, but the range should not be too wide so that too many things are happening and then you end identifying very little. So this is important. Very often in optimization experiments, the best known operating conditions are located in the center of the region, which is the average of the ranges, in this case, 32.5 minutes for the time and 200 Celsius degree for the temperature. So this is the real quality attribute function of this toy example. On the left-hand side, we see a contour plot. On the vertical axis, you have the factor 2, which is temperature, that goes from 175 to 225. On the horizontal axis, you have the time that goes from 25 to 40. What you see here is curves that they express the value of the objective function, so the quality attributed function, which is how good our process is. You have to look at this map as if you are looking at a map while you are hiking, and you see the contour plots that they tell you how high the hill is that you're gonna go. So this is the same thing. We have identified 5 points interesting in this area. And before we going to describe each point, on the right-hand side, you have exact the same function, but now in 3D, where the quality attribute function is now expressed on the vertical axis. So let's start with the points. A1 is the maximum, the global maximum. This is the point where the quality attribute function has the highest value. A2 is what is known as a local maximum. It's also a high value, but it's not as high as A1. Then we have the points B1 and B2, that they are global and local minima. And we have the point C, which is a saddle point. Saddle point is a point where it changes in every direction, either if it improves or it worsens. And you have to think to visualize that kind of point in a saddle of a horse riding. I mean, when you do horse riding, the saddle where you sit, that's a saddle point. Okay, let's go to trial and error. What happens there? So trial and error is an iterative process based on guessing and intuition. How does it work? So normally you start in an optimization of experiment at the center of the range, and then you will test there, see which quality attribute you get, and then following your intuition, guessing, and know-how, move to the next point. Then in this case, if you move to the next point, you will get a lower value, so you move on onto another direction, and then you will slowly improve your objective value until you cannot improve it anymore. So this could be one path, the one that I just followed in white, but this gray could be another path, And you see that this grade takes many more tests to get to this local maximum. But you could also have this one that takes another direction and ends in the saddle point. So not reaching the local maximum or the global maximum. So the presence of the saddle point can make things difficult for this trial and error, and the number of iteration depends a lot on luck. You don't have an estimation of the cost of the experimental effort, and the method doesn't work well when you have a larger number of factors. So what if we will do systematic data acquisition where also intuition is included, but where the points that we are going to test are decided beforehand? This is design of experiments. So we want to study what is the quality attribute function for different values of factor 1 and factor 2 within the square that you see here, so within the ranges that we have set. Using design of experiments, using just 5 data points, so the points at the corners and the point at the center, we are able to identify the global. As a summary, trial and error is an iterative process based on guessing and intuition. It is suboptimal. It produces a waste of resources because, yeah, you normally end doing many tests, so it has little return on investment. You don't create knowledge, so very little. You don't have guarantee of optimality, and you have a poor performance as the number of input factors increases. On the other hand, design of experiment is a systematic data acquisition where intuition is also included. You can make decisions with confidence, you use your resources optimally, you discover knowledge, you have a statistical guarantee that you will find an optimal recipe, or you will prove that no optimal recipe exists. You can quantify the experimental error, and when the number of input factor grows, the method stays performant. So next section about the 5 phases of a design of experiments project. This has been covered up to a certain extent in the previous webinar, so I will go fast over it. We have 5 phases. The first is the preparation, where all stakeholders, they gather and they define the conditions of the experiment, so which inputs or factors they want to study, and in which range, which outputs will define the performance of the product or the process, what are their specifications, and any other aspect that may influence the result. With all that information, we set up the experiment, which is choosing a smart selection of combinations of factor values to be tested. This is sent to the persons that are in charge of conducting the experiment, that gather the data. So you have on the one hand the experimental design, and then on the other hand the data gathered, which is the set of quality attributes of the product or the process. With that data, you go to model selection, where you replace the data with a mathematical model. Mathematical model, which allows prediction. So you could predict what will be the quality attributes value for given combination of factor values, even if you didn't test that specific combination. And importantly, the mathematical models, they also allow optimization. Optimization is traveling on the other direction in a mathematical model. So while prediction is starting from the factor values and predicting what the quality attributes will be, in the optimization, you first specify where you want your product or your process to be. So what are the quality attributes that they have to be fulfilled? And then you travel using the mathematical model on the other direction to see which combination of inputs you have to use. to reach that goal. Let's see how this works for the muffin experiment. So this is a schema of what the problem is there. So the different batches characteristics of flour affects the quality of the muffins. So we have the flour characteristics, and we also have the recipe and production process parameters that they will define the production process. And in the end, we will have a muffin with certain quality, which will be measured using some quality attributes or responses. So getting more specific, on this slide, you see on the left side a table with the recipe and production process factors. There are 5 factors. 3 factors are related to the recipe, the eggs, the butter, the flour, and 2 factors are related to the production process factors, so the time and the temperature. You see that we have specified the units and the range we want to study these factors at. On the right side, you find a table where we have the characteristics that define a batch of flour that goes into the production line. Those are the proteins content, the starch content, and the moisture content. So importantly, the factors that you see on the left-hand side are controllable factors. So this means that we have the freedom to change the factors within the range that we specify, while the factors on the right-hand side, they are uncontrollable. So we cannot decide the exact values for the protein, starch, and moisture content, but we can measure them. Finally, on this slide and this table, we see how we are going to measure the quality of the muffin. And we are going to use 4 different attributes: the taste score, the moisture content, the calories, and the cholesterol. So each one of these quality attributes has specifications. So it has to be either maximized, or it should be within an interval, or should be minimized. And you have the corresponding upper, lower, or both bounds. The goal is, of course, to be within specifications for all 4 quality attributes at the same time. Next step, next phase of the DOE flow is setting the experimental plan. You see it here. You see here how we have a table with 24 rows and 8 columns. So the first 3, they correspond to the batch of flour that is being used, and the others are the experimental factors. So this is a very small design. If you imagine that you will like to try all combinations between minimum, average, and maximum values of the 5 controllable factors, you will have to do almost 250 batches of muffins. So this is what design of experiment does. It selects a smart combination of factor values to be tested so that you gather the maximum information. So this is sent to the persons that are going to conduct the experiment, and they add the second table there on the right, which contains the values for the quality attributes for each one of the tests. So you see that the first has a taste score of 9.3, moisture of 14.25, calories of 333, and cholesterol of 127. As you see, this has an okay taste score, of course. It has a moisture that is below the lower bound, and it has too many calories and too much cholesterol as well. So you see there is trade-off between the different responses. Now this is being analyzed and optimized, and this is one of the graphs, the graph that I will show you during the software demo. This is a graph that is based on the mathematical models that we derived from the experimental data. This graph has 3 parts. Left part is the input space, where we have 8 different axes, each one corresponding to one of the factors. So we have the 3 uncontrollable factors first, and the 5 controllable factors afterwards. This you have to look at as a grid, I mean, because it is a grid, um, in the sense that one broken line from left to right indicates a specific combination of factor values. So if you will have a broken line that starts here, will tell you that you're looking at a sample with a content of protein of 985. If this line will go here, then it will have 73% of starch. And if we will go here, for example, it will have 13.5% of moisture. May go now here, which means that this specific combination of factor values has 70 grams of egg. It may go all the way down here, which means that it also has 28 grams of butter and so on until a temperature of 225, for example. So here there are 5 to the power of 8 different combination of factor values. And for each one of those, we use the mathematical models to calculate the predicted taste score, the moisture, the calories, and the cholesterol, which are the 4 vertical axes that you see here on the right-hand side. We have a third section. So after the output space section, we have this last section, which is the probability of success, and is a single numerical value that assesses how likely are you to be within specifications for all 4 quality attributes at the same time. And we color each line using that last axis. This is a highly interactive graph, as you will see, and it allows optimization and filtering as well. So here in this slide, you see how we have filtered the graph. So we have specified certain values for the protein, starch, moisture. So this illustrates a case where you will get a batch of flour into your factory with these content percentages. And then you see that we also have set a filter for the probability of success to be high. And the graph is telling you which values for the recipe factors and the production parameter factors you have to use to get a muffin within specifications. So such a graph and the mathematical models the graph is based on allows you to have a robust production process. Now I'm going to switch to another tab to show you the graph in action, and this will end the presentation. So I'm going to switch to the software. So here we have it. We have already set the specifications for each response here, the specifications limits, and this acts on the graph that you see on this tab. We can change the discretization, so we can do discretization of 2 or discretization of 3, 5. We can also increase it. Of course, the more discretization you will do, the best you will explore this multidimensional space. Now, the example that I told you, let's say that we have a value of protein of that value, we have starch of that starch content of that value, and we have low moisture content. Then you see that a few lines they survive, and if we will filter it with only allowing points with a high probability of success, it will give you the combination of factor values that you can use to still get a compliant product. So this graph can be used for robust optimization, in this case against raw material variability. You can do quite a lot of things with this graph, and I'm going to show you another one. So let's say that you want to study what happens with content of protein and starch and that they lie within these ranges. So instead of going within the original ones, well, better let's do something different. So we're going to fix the value of protein content, value of starch, and the value of moisture. And we are going to set some constraints on the egg content and on the butter. Let's say that the butter is very expensive, so you want to keep it low. So we can click consume. And here you see that for those combinations, you actually cannot use these values. So let's come back. You see that we have fixed the flour characteristics, and now we have still some values that they are surviving. So we have to go for a high amount of butter, and we have to go for example, low amount of flour. And we can have here a high amount of eggs. We can click consume, and you see how now the discretization occurs within the ranges that we have set for each one of the controllable factors. So this graph allows you to find a window where any value of the factors will produce a compliant product. We have a table here that gives you also the best combination of factor values for this specific filtering. So we have shown how we use an interactive graph to solve this robust problem of the muffin company. And this ends the presentation. So I am now at your disposal for any question, comment, remark you may have. So thank you for your attention, and yeah, hope to see you soon.
So if there are any questions, now is the time. You can put them just in the chat if you would like, to do it that way, or you can just like unmute yourself and ask the question. By default, you will receive the presentation and also the recordings of this webinar. And we are always at your disposal for extra questions, or you can always email us or go to the platform or to our website fx.app, where you can also ask for more information or book a demo, or find some more information about FX, about our platform, about design of experiments. And you can also find a lot of use cases on our platform and on our website on design of experiments.